Now we're going to talk about pressure sensors, how they've been used at an very active underwater volcano in the Northeast Pacific, Axial seamount. And it's unusual in that it's got a long time series of these measurements. Here's Axial in the Northeast Pacific. It's about 500 kilometers offshore. Here's the subduction zone that we've been hearing about in some of the earlier talks. Axial seamount's out here on the Juan de Fuca Ridge, which is a tectonic spreading center. So the plates are moving apart out here. So there's volcanism all along the plate boundary, but there's also a hot spot located here, which is has helped all these seamounts grow that are off to the northwest. So Axial is the current location of that hotspot that's more or less superimposed on the Juan de Fuca Ridge. So it's got an extra magma supply that's why it's so active. So zooming into the summit here, there's a caldera at the summit, a big crater. It's about 3 kilometers wide, 8 kilometers long. The caldera walls are 100 to 200 meters high. And the seafloor here is about 1,500 meters deep. The volcano itself is about 1 kilometer high above the deeper seafloor around it. So it's the most active volcano in the Pacific Northwest with 3 eruptions in the last 25 years. That's one of the reasons why it's so interesting to study. I'll just say that volcanoes have the advantage that the deformation signal that we're interested in is very localized. So in contrast to subduction zones where the deformation spread over hundreds of kilometers, at a volcano like Axial, most of the deformation that we're interested in, is within the caldera here. So that has some advantages for how we can take out some of the noise in the pressure data. Okay, so just some cartoons between eruptions. We think at volcanoes like Axial, basaltic calderas, magma's rising and accumulating in a reservoir beneath the caldera. So that is making the seafloor rise. So this happens slowly and gradually. And then during eruptions, that accumulated volume erupts onto the seafloor. So it's removed from this reservoir and the seafloor falls back down. So this has been known at volcanoes on land for a long time. Here's Krafla volcano in Iceland, Kilauea in Hawaii. These are a few time periods when this deformation pattern is very repeatable. It's not always that way. But here's the ground gradually rising between eruptions or intrusions and then suddenly dropping back down, making this kind of sawtooth pattern. So that's the kind of thing we want to see at Axial seamount. Okay, so that's what we want to see with these pressure measurements, vertical movements, the inflation deflation cycles. That gives us information about the timing of magma movements, the rate of magma supply, volumes in and out of the reservoir, and the depth and geometry of the reservoir, all those things we're interested in. If this sawtooth pattern is repeatable, it could be used to try, a way to try to forecast eruptions. So challenges, we've heard some about this in the earlier talks. In the short term, if there's a large sudden event like an eruption or an intrusion, those are easy to detect with EPRs because you don't have to worry about drift or oceanographic signals. It's because of the short duration, and they're usually large, so that's easy. But we're also interested in the long-term reinflation at lower rates, which is can be at the same rate as drift and so forth. So that's a challenge that we have to deal with. And and also the oceanographic noise, which we've heard some about already. So the way we've gone about doing this at Axial seamount is use a combination of bottom pressure recorders, which are continuously recording. So we convert the pressure to depth, remove a predicted tide signal. But the way we deal with the long-term drift problem at Axial is we also use what we call a mobile pressure recorder that we connect to a remotely operated vehicle. And we set out these seafloor benchmarks in an array, and we make repeated measurements with the NPR at these benchmarks in a campaign style every few years. And this gives us the relative depths of all the benchmarks relative to a reference site that we put outside the caldera where we don't think much deformation is happening. So this can also constrain the drift of the BPRs that are co-located with those benchmarks. So here's some time periods of different measurements. Here's co-eruption deflation. So that's the seafloor going down during the 1998 eruption. Inflation, you can see the number of measurement points has increased with time too, as we've had success and want to know more. Here's inter-eruption inflation. These are all in meters between the decade 2000 to 2010. Another eruption in 2011, deflation, inflation again up to 2013 in this case, another eruption in 2015, and then 2015 to 2020. So there's like 9 benchmarks in the caldera. We've added a few since then. These red ones are connected to a cable to shore, which I'll talk more about in a second. So I wanted to just point out that the patterns are very similar in all these time periods, where the maximum uplift or subsidence is always near the center of the caldera, and the least uplift or subsidence we see out to on the eastern flank here among these benchmarks. So I just talked about this cable that goes all the way to shore. This is part of the Ocean Observatory's initiative. They call it the Regional Cabled Array. So a cable comes all the way from the Oregon coast out to axial seamount. There's a whole network of instruments connected to it to monitor the volcano. Among the instruments are 4 bottom pressure recorders encircled in red here. And I have a website where real-time data from axial seamount is plotted. Kind of amazing. So this is detided pressure converted to depth. This is a week's worth, the last week's worth of data. So the ups and downs here are tidal residuals. So our tidal model is not perfect. The green is temperature. The red is the detided depth. All right, so looking at a little same kind of data over a longer period of time. This is 3 months now. So this is the instrument at the center of the caldera that we know moves up and down the most with our geophysical signal. This one is from this instrument here on the eastern flank that we know moves up and down the least. And so in these records, you can see there's plus or minus up to 5 centimeters of tidal residuals, this high frequency stuff, and then the longer kind of weeks to months signal, that's the oceanographic noise that we're not interested in this case. But you can see between these 2 sites that are only 5 kilometers apart or so, that noise is very coherent. So we figured out that if we subtracted this one from this one, it takes out most of that noise and leaves a much better representation of the geophysical signal that we're interested in. So in this case, we see a little minor deflation event that we know is real because the seismicity at the time also decreased at exactly the same time. So here's the longer term record going back 25 years, the 3 eruptions with the big deflations. I should say that Axial, one reason why Axial is a great place to work is because the signals are so big. This, subsidence of 2 to 3 meters. Here's reinflation. The purple dots are those mobile pressure recorder measurements that we use to tie all these together. The Cable Observatory went live in about 2014, late 2014. So all the data since then can be one continuous record. Before that, these were deployments of a year or 2 or 3 that were stitched together using these the mobile pressure recorder data. Okay, so we can take this record and look at the rate of inflation and how it's changed over time. That's what this plot shows. So I've used a 1 year long moving window, so getting a really broad average rate. And the blue line is how that rate has changed with time. So it's initially high, got low, increased coming up to the 2011 eruption. We think there was a surge in magma supply in this time period because the uplift rates were very high, and that's why these 2 eruptions are closer together. And then since 2015, it's dropped way back down and is very low at the moment. So just zooming into just this part of the time record since 2015. Now I'm showing in red data from a single BPR station. And in blue, I'm showing the differential BPR record. So that's going back several slides where we subtracted the station to the east from the one in the center. That's our differential BPR record. So that presumably removes the oceanographic noise, whereas it's still in the single station data. So an interesting thing we noticed was that since this is differential, it's one relative to another, we have to multiply it by some empirical number to make it approximately equal the uplift rates at the center. So we've also done that. Otherwise, they wouldn't be the same. But if we compare these two, that's the corrected part of this. You'll notice that the single station record deviates from the differential record every fall and winter when it's going above the red line's going above the blue line. So that's a seasonal signal. And so there's apparently a seasonal lower pressure time period when the apparent uplift rates are higher than they really are. So just some thoughts about some opportunities. We don't really understand what that is from, but here's a sentence that Rick Thompson of Ocean Network Canada helped me craft in the recent paper about the possible reasons for that. Stronger wind force bottom currents flowing over the sensors in the winter versus summer, dynamic air pressure forcing that may have seasonal amplitude, and pronounced seasonal shifts in circulation and water masses of the California current system. Now, I'm a geologist, so I don't understand any of that, but some of you probably do. And I just brought it up in case it inspires some interest in any of you. Happy to share data, and that's an open question, I think. Another use of this data, because of the long time series, Rick Thompson and Isaac Fine took advantage of this to look at the frequency of tsunamis in the Pacific. And so there's certainly other uses for this data set that are possible. And the one that I'm personally most interested in is learning more about the magma reservoir at Axial seamount. And this is an example of some ongoing work by Sandra Salid, who's here. And I think she'll be presenting this at the poster tomorrow. This was a poster she presented at AGU this year, doing some modeling with Matt about how our pressure data can constrain what we know about the reservoir. So that's all my talk.